Hey, it's Hawking with Topdon. We're back today. We're going to do dynamic battery and starter testing, and we might do alternator if we have time. We'll see. But today we're going to cover dynamic battery and starter testing with the Topdon oscilloscope. So, a lot of folks use standard various testers. Any of the different testers out there for quick checks on the battery that can be used just for a quick initial, hey, is it good or bad? But sometimes you get a result that is inconclusive. So when you get those results that are inconclusive, a lot of technicians struggle with where to go next. So, what can we do to pinpoint whether or not we have a failing battery? Now, there's a lot of different ways you can do this. You can buy a carbon pile load tester. You can also buy, you can also use an oscilloscope like we're going to do today. Now, there are a number of different preconditions we want to be aware of when we go into dynamic starter testing. And we're going to actually pull up some slides here, and we're going to walk you through some of that specifically so that we can address those in detail. Because we want to make sure we have a good foundational understanding of what we're going to do with the test before we go and demonstrate and actually perform the test, right? It's important to understand what the test purpose is, how we perform it effectively and accurately, and what it means before we attempt to go and perform it, right? Hopefully that makes some sense. So I am going to see if I can get this to share screen. Okie dokie, there we go. Perfect. So hopefully now you can see my screen. We are going to do a slideshow just briefly here and walk through just a few things talking about the dynamic starter and battery testing as it pertains to doing it with an oscilloscope. So when it comes to the basic setup parameters, these are for your reference, so I'm not going to talk through them. You'll have these on the video so you can go back and reference them again, and we're going to live demonstrate it, so don't get too hung up on reading these right now. But essentially, when we do the test, we're going to want to have a fairly decent amount of time on the screen so that we can see what's happening, the overall time period of the cranking event. Now, as far as the sample rate of the scope goes, turning it down can help you cut down signal noise, and we'll demonstrate this as well so you can kind of get a feel for what effect that has on the waveform. The good news is that you don't actually need a very high sample rate in order to do this test effectively and accurately. Now, why does that matter? Turning up your signal or your sample rate, excuse me, is actually going to add noise to the signal. So it is important to understand that sometimes if we turn up the sample rate to an unnecessary level, the only thing that's really doing is adding more noise to the signal you're capturing. So we're going to use two channels when we do this test. We're going to basically use one channel that we're going to place across the battery. So when we do this, we'll show you exactly what we're talking about here, but we're going to have one channel across battery positive and battery negative. The second channel we're going to place on an amp clamp, and that amp clamp is going to be placed on preferably the cable that goes to the starter, the positive cable. If that's not possible, then you may have to alter your strategy and put it around the negative cable. And we'll show you what happens when we do this so you can understand how the waveform is impacted, as well as understanding what exactly you need to do to address this in order to get the correct data on the screen, so to speak. Now, the other thing we want to do when we're performing this test, and generally most tests we do, we want to make sure we turn on the low pass filter. Now, depending on which version of the top-down scope you have, you'll have either a setting that says 20M as in Mary on the channel settings for filter, or you will have something else that reads high pass, low pass, and then 20M as in Mary. You can use the 20M as in Mary or the low pass setting on version 1 of the scope. Version 2 will only have the 20M setting. So that's the one you want to turn on each of your channels before we go to do the capture. Now, here's some additional things you want to keep in mind before we get into the actual testing. So again, if you're just joining us today, we're talking about basically performing a battery dynamic test as well as a starter test using a Topdon oscilloscope. Now, the other thing we want to keep in mind is there are two ways to test this battery. When we bring the vehicle in initially for service, or this is our own personal vehicle, it's a good idea to perform this test once before charging the battery, just to see, especially if we have any electrical symptoms. So, a good example would be if you have someone who's reporting or you are experiencing a slow cranking condition, or you have a bunch of lights on the dash, maybe some U codes when you scan the whole vehicle for communication, or you have voltage specific fault codes in various modules, then it may make sense to go ahead and do this test once before charging the battery. See what the results look like. Then, after doing that, you may want to recharge the battery and perform the test a second time. If we get dynamically different results between the before we charge it and the after charging it result, sometimes this is a good sign that we may want to be checking for a battery draw. So in those cases, perhaps communicating to the customer, your battery was pretty low on charge when it came in. We recharged it, and now the vehicle starts great. Maybe this is time to then sell a draw test and perform a draw test on the vehicle. If we're going to do that, we also need to make sure that we pre-scan the vehicle before we do any of our tests, so we have documentation on that. And you can actually take the scope captures like we're going to do today, and we can embed those into the pre-scan report. So we're going to try to demonstrate that too if we have enough time. The other thing you want to keep in mind here, as we're doing this dynamic test on the battery and the starter, is the results can change depending on how many times you perform the test consecutively. So let's say, for instance, we have a battery that we think is marginal. We've performed the full recharge of the battery, and we think that there's still a problem. Sometimes we could perform this test multiple times in a row. And when we go to do this test multiple times in a row, if we start to get different results over time, in other words, let's say our battery voltage starts to fall pretty steeply, or we seem to start developing a problem cranking the engine over, that can indicate a number of different problems may be present, right? We could have an internal problem with the battery. We could have a point of high resistance in the wiring harness, somewhere going to the starter or the battery, which is a good time and opportunity to pick out our thermal imager and take a look around to see if we have any connections that are building up heat. If we have excess resistance in any of the wiring or connections, we can pick that off with a thermal imager. However, a lot of the time, we're going to have to perform that cranking test multiple times before we're going to pick off that buildup of heat. So again, just keep that in mind as we go through the testing. The other thing we want to do before we do a cranking test is we want to do a quick 10 seconds on, 10 seconds off of the headlights to remove any surface charge of the battery. That's always a good policy. It's also important to understand what the battery chemistry of the vehicle is. Now, every vehicle is going to be different. Some vehicles are going to use a standard flooded lead acid battery. Some vehicles are going to have a EFB or enhanced flooded battery, and those behave a little bit differently than a standard flooded battery. Or they may also have an AGM, absorbed glass mat, or it's possible they may even have a small lithium 12-volt battery. So, depending on what kind of a cranking or starter battery your vehicle is equipped with, it's important to understand what the normal resting voltage, so resting voltage being no current is being discharged from the battery. If the vehicle is fully asleep and we have all the doors locked and we trip the hood latch sensor out, because a lot of vehicles now have a hood latch sensor, if we trip all those sensors out and we put the vehicle to sleep, our static voltage, basically the voltage we measure across the battery, there's going to be a specification depending on the particular type of battery chemistry you're using. So if you have an AGM battery, the normal resting voltage that represents a fully charged battery is a higher voltage state than what you would see on a normal flooded battery. And if we go to an enhanced flooded battery, those also often have an even lower resting battery voltage under normal conditions. I have personally verified this on several vehicles with the enhanced flooded batteries, where sometimes you go to check them and the resting voltage is around 12 volts flat, which on a normal flooded battery or an AGM battery, that would be a very low state of charge. So again, what's normal for the given battery you are dealing with may be different. A simple tip if you're trying to find out what's normal, Check the service information from the vehicle manufacturer first, of course. Also, if you do a Google search and you simply type in the type of battery, so AGM, state of charge, table, you can find this pretty easily, and you want to check a couple of different tables to make sure that they agree with each other. But generally speaking, that's going to be a pretty reliable method of finding what a normal resting voltage is for a given type of battery. Okay, so again, if you're just joining us here, we're talking through some of the foundational stuff we need to be aware of before we perform a dynamic battery test or a dynamic starter test. Now, again, like I already mentioned, doing the test more than once consecutively can help reveal possible faults that don't show up on an initial cranking state. So just keep that in mind as you work through the test. Now here, we're going to show you a known good waveform. There's no problem with this particular vehicle that we're displaying here. We just want to talk through the waveform a little bit so you have some understanding of what we're physically seeing on the screen. So in this capture, you can see we are zoomed into 500 milliseconds time. So you can see it doesn't take very long for the engine to start here. That's what we're looking at. Oh, a few hundred milliseconds, basically. Not much. Now, the other things we're looking at here when we do the test, number one, our battery is pretty close to fully charged. We're at 12.52. This says 12.62, but you can see here where the line we have drawn on the screen, this cursor right here, the Y2, that is at about 12.62. So it was fully charged before we did the test. Now, the other things that we look at closely when we do a starting test is we're going to look at how low the voltage drops at the initial cranking instant. So that is what they call when the inrush current or maximum current flowing to the starter takes place. That's when the voltage is going to drop the lowest on the battery. Now, some of the things we want to keep in mind that are important here with respect to what we see in the voltage. In the voltage waveform, we want to see that battery voltage recover pretty quickly. So you notice how the battery voltage comes back up pretty quickly. It doesn't stay down here. It doesn't go very low. It doesn't go very low initially, nor does it stay low for any long period of time. We also see in the current drawn by the starter, which is this bottom waveform, we get a big inrush of current to overcome the momentum, the inertia of the engine rotation. And then the current drops off pretty severely, roughly to about, just a little under half maybe. And then from there, as the engine continues to rotate, it tails off accordingly, which means, number one, the engine started correctly. And number two, we have good connections. We also have a good battery. We have strong current flowing to the starter. And we know the engine cranks over and starts, which is something we can also verify auditorily. So using our hearing as a skill, when we do a cranking test on a battery and a starter, we can listen for that cadence. And you'll hear on a normal vehicle that that vehicle cranks over very even. It cranks over relatively quickly, and you get ignition and fire pretty quickly as well. So you can hear the engine start the combustion process pretty fast. So again, we'll do it on a known good vehicle on the video today. We're not going to do a broken car, but we're going to show you what you're looking at. Now, how much inrush current is going to vary based on vehicle? I've seen lots of different tables or general recommendations. I've never seen a specification published by a vehicle manufacturer. What I have seen as a general statement is I've seen four-cylinder engines anywhere from 300 to 600. I've seen six-cylinder engines usually a little higher at a floor, so 350 or 400, maybe all the way up to 700 and change. I've also seen vehicles that are exceptions to this. So the inrush current is not necessarily something you can live or die by unless it's way outside normal. So if you have, let's say, a four-cylinder engine and it's flowing 1,000 amps of current, that's something to be concerned about. Now, it's also important to note whether or not that current falls pretty dramatically. If that current does not fall off pretty dramatically relatively quickly, that's going to be a sign that you may have mechanical binding in the engine, right? So current flow is a direct representation of physical resistance. There's a direct one-to-one relationship in the way the waveform looks versus the mechanical resistance that the engine is facing to rotation. So here, it takes a lot of force to overcome the inertial movement of the engine to get it rotating. And then as the engine starts to rotating, it takes less current to keep the engine rotating by the starter until the engine starts. And then, of course, it switches off the starter, at which point now the engine is running. So again, understanding that relationship between the current and the mechanical resistance of the engine is important. Now, voltage, on the other hand, as far as our battery dynamic test, is something we can pay a little closer attention to. Generally, most vehicles that I have performed dynamic starting tests on with a battery test, I usually see the voltage drop about 3 volts from the point at which it starts. So if it's 12.62, all the way down to 9.62 at its lowest point would generally be something that wouldn't concern me. Now, again, I'm still looking at those other characteristics in the waveform. But again, we want to make sure that we understand that 3-volt drop is pretty normal. Now, I have also seen vehicles where the voltage drops a little further. I've seen as much as 4 volts of drop. Now, 4 usually to me, if we have a symptom, we have a concern from the customer, if we have a 4-volt drop, that's typically a sign there could be something going on there, which is, again, why we want to repeat our tests multiple times to make sure that we can replicate the results, to make sure we didn't screw something up, and another reason why we want to perform the test both before charging the battery and after charging the battery, because that can help you understand and reveal those issues. So here are some general things we're looking at. Again, if the voltage falls under 9, that's generally a sign that the battery may be failing. However, again, that's a function of how much voltage the battery starts with before we begin the test. If that battery is not fully charged to 12.6, 12.8, whatever kind of battery state of charge chart you find, if it's not fully charged before you perform the test, then that 9-volt threshold is no longer applicable. Once it's fully charged, a 9-volt threshold is generally a reasonable threshold. Now, again, I've seen vehicles that drop a little lower than this, down to 8 and change, and they've been completely normal, which will actually show you an example of this. So just keep that in mind because, again, it's very important to understand that the amount of drop in voltage on the battery is also important to recognize that that's relative to how much voltage the battery starts with before we crank the engine. Now, here's our capture on another vehicle. Now, this is a vehicle with an enhanced flooded battery. Do you notice how our beginning voltage before we start the test is unusually low? We're beginning at only 11.2 volts. That's pretty low, right? Number one, we should probably recharge the battery before we do this test, right? And number two, if we look at the drop in voltage, we still get a normal drop in voltage of 3 volts. So even though this battery is at a low state of charge, we can see that the battery, number one, still only drops 3 volts when cranking. And number two, that current falls off just like it should from the starter. And the battery still seems to recover voltage relatively well. Now, keep in mind, we are zoomed in at a closer time base here. We're at 100 milliseconds instead of 500 milliseconds. So your subjective perception of the shape of the waveform is going to look a little bit different depending on how close you're zoomed in. But the key things we're paying attention to here, number one, our inrush current is still pretty normal. Now, this was actually a 6-cylinder. And you can see our inrush current was 560 amps at the highest point. You can see our voltage only dropped 3 volts. And you can see our voltage recovered reasonably quickly. And everything smooths out and the engine started. So we have no symptoms and no concerns. So even though we fall to a lower level of voltage and we're beginning at a lower voltage when we crank the engine, this vehicle starts perfectly fine and there are no symptoms present. And that is because this vehicle is an enhanced flooded battery. And again, enhanced flooded batteries are actually more like a deep cycle marine battery. So they have more ability to handle greater states of discharge on a regular basis, they also can continue to perform even in a more discharged state than what you will typically see out of a regular flooded battery. So again, this is why it's so important to understand what battery is installed on your vehicle before performing this test. So again, here's your notes about the last slide. So again, we performed that test on this last slide here on an enhanced flooded battery vehicle. And it is really important to also understand that on some of the newest vehicles you see out in the field, the alternator is actually getting duty cycled off. And I mean completely turned off while you're driving down the road. That means that the battery may not be getting recharged as aggressively or as fully when you are driving down the road. That means that when you shut that vehicle off, the resting voltage of that battery may begin at a much lower level than what you would have classically anticipated on a normal vehicle. So keep that in mind. The other thing you want to keep in mind is many modern vehicles today, regardless of which battery chemistry they're using, have adaptive charging systems that have an algorithm that frequently needs to be reset when you do any kind of battery replacement. Now, keep that in mind. The good news is if you have any of the Topdon Phoenix series professional tools, those tools can generally handle that task without any difficulty. So if you are replacing a battery, make sure you are looking in service information to determine which module is in charge of controlling the alternator charging status, and then looking in the special functions menu on your Phoenix scanner to verify if there is a reset function present. Okay, so that concludes our slides section. So we're going to switch back over here. I'm just going to look and see what we got for questions. One moment. Good question. So we've had some questions on how to determine which version of the scope you have without hooking it up. And we have actually researched this pretty thoroughly and have not been able to determine any clear criteria that tells us which version is which. And I'll show you on the camera here just a second. We've checked. We've looked at on the manufacturing side. There is a number here on the scope, and you can see there's a serial number and a version number listed. And even after going through all of the ones that we have, I actually have both versions of the scope. Even after going through both versions of the scope, I have not been able to find anything hardware-wise on the outside of the body of the scope that clarifies which one is which. We've actually asked our manufacturing department about it, if they have any clarification, and they've said they don't have any documentation that clarifies which hardware version is which. So at this point, the answer is no, unfortunately. You basically have to plug it in to know which version you're using. Now, the good news about that is all of the scope versions that we offer currently have a very similar user interface. Yes, they are not identical. However, they are very similar. So what I'll do now is I'm going to switch over my camera so you can see. I've got a camera set up on the car, but I'm going to switch over to the Phoenix Max first so you guys can see this. So this is one version of the scope here. And this version of the scope, basically what we can see, and of course now it's going to be a jerk and potentially cut out on me. I had some issues with this last time, and I'm not sure why. But as we look here on the scope, if we open up one of the channels, when we're looking at the channels, we can actually see down here at the very bottom, there is a bandwidth section. So on one version of the scope, you'll have a bandwidth toggle that has 4 options. On the other version of the scope, you will have a bandwidth toggle that only has 2 options. That is the easiest way to differentiate between the two. Now, again, I could not say why it is that there's 2 versions that we can't more easily identify from the hardware differences. That one, again, continues to stump me. But again, what I will say about it is, yes, they are, in fact, almost identical in all respects, other than that channel filtration element. So outside of that, most of the other controls that you see on the scope are going to be pretty similar. So I'm just going to turn on the low pass filter for each of the channels here so you can see I'll get all set up. Now, the other thing that we're not going to demonstrate today, but perhaps on a future one, is it is possible when you are using the scope and doing this test you can also, if you're wanting to, you can also put additional leads on the vehicle to more closely pinpoint if you have an issue. So again, when we talked about initial setup, we're going to go to the car, we're going to hook up one lead across the battery, and then we're going to hook up an amp clamp at the starter cable, right at the battery, either the positive or the negative, whatever's easier to access. But again, keeping in mind that if we wanted to go deeper on this test and get more precise information about what's broken, whether it's a wiring problem or a starter problem, we could add a third lead or a fourth lead. And when I say that, the third lead we could add is we could add a lead that goes right to the primary feed, the positive feed to the starter itself, the motor. We could add a lead there to monitor voltage there. We could also add a lead to the starter solenoid positive feed to check that. And if we wanted to, we could replace one of those two extra channels and look at the ground going to the starter, which of course is fed through the engine block. Starters don't typically have physical grounds. They ground through the engine block, which of course runs through a cable back to the battery, right? So just understand that if you want to prove out where your problem is coming from, you can enhance this basic test a little further just by adding some additional channels. So the first thing we're going to do is let's go ahead and go get hooked up to the car. So I'm going to switch over here and you guys are going to see me doing some stuff here. Now, if I can find my, I'm just going to go over here and grab my cables. And I wanted to not preset this up because I wanted you to actually see me do it. I know a lot of people don't like webinars where everything's preset up in advance. And then, of course, you know, the instructor doesn't actually really demonstrate anything. They're like, oh, I already did the work. Too bad, right? So, all right. So remember on your Phoenix scope, you can kind of see in the picture here just a little bit. On the scope, the channels go the opposite direction on the physical hardware. So channel 1 is actually going to be on the far right of the scope. And when I go to plug it in, of course, you're going to get some signal noise there. That's pretty normal. Also, keep an eye on your signal noise. You may have a bad lead if you do get a ton of extra signal noise. I don't believe this lead is bad, but we're going to find out real quick here. So remember what I said. For channel 1, we're going to go across the battery. So in doing so, I have a charger on it right now. I'm going to stop the charger. I've already recharged it. And that was because I wanted to show you a known good car. This vehicle does not have any symptoms of any kind, just so you know. Okay, so we're going to take our charger off. Charger is disconnected. Everything's good there. We were using the T120 to recharge it, just so you're aware. So again, here's our negative over here. Oh, and my alligator's going to pop off on me. Now, actually, on this one, I'll just do that. These ones kind of have this nice little section right on the battery cable where you can clamp on like that and get a pretty good grip. So keep in mind, if you're not sure which cable is which, you can always look at wherever one of the cables connects to the body of the vehicle. That's going to be your ground or your battery negative feed. So now you can see my voltage on the screen. We'll switch this here so you guys can see this. And it's important to understand you may have to adjust your scaling on your channels. So we'll switch over the scope so you guys can see what I'm doing here. You may need to adjust your scaling on the scope. And what your scaling is set to is going to affect the resolution or clarity of the image you capture. Now, the other thing I'm going to show you here. So again, we talked about sample rate, right? We're going to go to menu. We're going to go to user set. We're going to lower it down to, we're actually going to go to, that's pretty good. So we're going to set it to 100,000. Now, again, if you watch this parameter here in the top of the screen, the sample rate in the top left corner there, one of the things you're going to notice is when I change the time base, so if I shorten the time base, do you notice that it changes our effective sample rate? So you see how it says 10,000 samples per second? Watch what happens when I change it back to 2 seconds on the time base. See how it cuts it down? Now it's 5,000 samples a second. So it's important to understand that when you manipulate the time base down here at the bottom, that's going to affect your effective sample rate. And again, we can increase our sample rate under the user set section under the menu if we want to. We're set to 100,000 right now. So again, just keep that in mind. That will affect what you're seeing. Now, we're going to shorten it up to 1 second. The other thing we want to keep in mind here is we have to set our second channel, which is going to be an amp clamp. We have to set that up for amperage. Now, if you are not sure how to scale your amp clamp, if I've got all of my stuff here, which I believe I do, we're going to show you a real quick and easy way to scale your amp clamp. And this is something a lot of people struggle with. So hopefully this is going to help you. All right, so got the amp clamp here. I'll show you. So I got the amp clamp here. You can see me over here with the amp clamp. I'm going to connect that to channel 2. And as we go through this and connect it, you're going to ask yourself, well, how do we know what the amp clamp is supposed to read? Or how do we set the conversion? Because remember, amp clamps don't actually create a volt or an amperage reading. They use the magnetic field to create a voltage output, which gets calculated as amperage. So if we switch this over to current instead of voltage, you'll notice that the only thing that changes is our display. Now our display reads in amps instead of in voltage. But we don't know. You notice how it says the multiplier here on the screen? So we'll switch over so you can see this. See how we've got it set to current now instead of voltage? We've got a multiplier here. So we have a 1 times, a 10 times, 100 times, or 1,000 times. What does that mean? That's the conversion that the software in the scope is using to physically determine what the voltage output of our amp clamp is and what that actually converts to so that the scope can accurately represent the measurement number. Again, the scope does not actually display real amperage. It displays the voltage output from the amp clamp itself. So what we're going to do is I'm going to grab a bulb, and I should have one here that I can use. So I'm going to grab something like a headlight bulb, something that we know the rough amount of current flow. So let's say, you have a fog lamp, you have a headlight bulb, a sealed beam is always an ideal one that you can use. And what we'll do is we're simply going to take that sealed beam bulb and we're going to hook it up across the battery. And then we're going to stick our amp clamp on it, on one of the 2 wires. And as we do this, this is going to allow us to determine the scaling of our amp clamp. So just pardon me for a second, I'm just going to get out my leads here, and I have a bunch of them, so just want to make sure we get them hooked up. So I'm going to switch over so you can see what I'm doing here. Okay, so I'm just going to take this fog lamp bulb right here, just going to set it on here, and then I've got some jumper leads, and I'm simply going to take my jumper leads, and we are going to connect one, and make sure you're not touching the body ground, right? Don't want to accidentally short this out. We'll go here, get on the battery, okay? And then we're going to go here. We'll take our second lead here. And you're going to see why this is a useful skill to understand, because again, this is one that a lot of people struggle with. So now we're going to connect to ground. And again, we're going to make sure we're not touching the body or anything else. Don't want to accidentally cause any arcs. Come on, stop it. There we go. And of course, that's the ground side, so we're not as concerned about it. We'll fold it under. How about that? So now, get a little bit of an arc when we first touch it there, but nothing too extreme. So now we've got our bulb powered up. So you guys can see the bulb's powered up. So now what we're going to do is we're going to switch on our amp clamp, and we're going to go over here. I'll leave it on 1 times for the multiplier for the amp clamp. We're going to stick the amp clamp around the wire and see what it reads. So what do we read for current flow on the amp clamp? Now, assuming I did everything correctly here, we are going to have a measurement. I'm just going to play around with the settings here until we have the correct amount. Now, the other thing you can do is when you are setting this up, we'll change it over here so you can see. You can actually go into the menu and hit the measure button, and you can select a channel, and then you can say, hey, I want to see the high and the low, the min and the max, the amplitude of the signal, whatever it is that you're looking to measure, you can find out. So depending on how I have this scaled, look what happens. So if I have it on 1000 multiplier, we have 90. That's kind of odd, right? That can't be right. We don't have that much amperage flowing to a tiny little bulb, right? What about if we change it down? Now, I did not zero my clamp correctly. So if I zero my clamp correctly, now you'll watch. If I hit run, stop. Now I got to zero this clamp. So I'm going to zero the clamp until it reads 0. Again, the clamp is not on anything at the moment. Now, some clamps have a zeroing function. Some clamps do not. Every clamp is different. You may need to do a calculation. So if you play around with your amp clamp and you're like, hey, I can't get it to really zero, the other thing you can do, obviously we're going to play with our scale a little bit here. So we're going to go down to a low scale until we're real low, and we're going to see what we read here. So I'm just going to crank it down, and you can see that my reading changes as I manipulate it here. And we want to get this until it reads 0. So you got to see our scale is down to 1 amp right over here. Whoops, turned it off, sorry. So we just get it down until we read 0 or real close to 0, right? Almost there. Now again, every amp clamp's different, so some of them are not going to zero out real well. But we want to get it as zeroed as we possibly can. And once we get it all the way down as close to 0 as we can, we're looking here, because we're looking at the minimum reading, right? Which naturally is going to get right in the way of my reading. And we're pretty close. So this one doesn't quite zero out perfect, right? Our minimum's like 200-ish. Now again, remember that's a function of the multiplier. So do we know if we're on the right scale yet? We don't. But if we go over here and we go around the cable, we'll make sure we face the clamp the right way. If we go around the cable, what do we read now? Now we read 4 amps. You see our max switched up to about 4. And I think the amp clamp is maybe having a problem here. It seems to be having an issue. Let's see here. Yeah, our amp clamp's definitely having an issue today. So that's lovely. I think it'll still be good enough, but essentially we are in the correct scaling, right? So if we change this multiplier here and we switch it to 1000, watch what happens, right? We're going to hit run. We're going to hit stop. Okay, we're back here. If we look at our ruler here, we'll zoom in a little bit more. We'll go down to a lower scale. Okay. Now what happens when we stick the amp clamp around this cable? Current goes up. Okay. What do we read now for a max? Around 8 amps, which seems kind of high. But again, that's a function of whether or not this is scaled correctly. So again, the only thing the scope is really doing here is making a calculation based on what we do. So this calculation is a function of our settings, nothing more, nothing less. Now again, that voltage or that amperage looks a little high to me, but it's still in the right general range, right? Because if we had a different multiplier here, watch what happens when we play with the multiplier. Change that multiplier. Now we have 860 milliamps. No, that can't be right, right? The bulb is drawing more than that. Change the multiplier to 10, 86 milliamps. No, definitely not, right? that bulb is going to draw generally around 4 amps. So even though this is a little bit off on the accuracy, probably because we didn't zero our clamp out, or it wouldn't zero all the way out, what we can say, whoop, stupid thing is trying to melt the wire. What we can say about it is that regardless, we are in the right range. And that's what we ultimately need to determine here, is if we're in the right range. Once we're in the right range for this particular signal, now we know our scale is correct on the clamp. And once the scale is correct on the clamp, now we can actually conduct the test. So I'm going to get this bulb out of the way here, and we are going to put our clamp in the appropriate place on the vehicle. I'm just going to set that bulb on the floor because it's a little hot. All right, so we have now got our clamp scaled correctly. So we are going to ideally try to put this around the starter cable. On this vehicle, it's not so easy, so we're going to stick the clamp around the negative battery cable. Make sure our connections on voltage are good. I'm also going to open my garage so I don't die when I go to do this test. I'm sure we can all agree that's good practice, right? We want ventilation when we do this test. Now, the other thing we want to keep in mind here is when an engine cranks, our current is going to go pretty high, right? So you notice our scale is set to 5 amps per division right now. We're going to need to change that quite a bit higher. So what did we see on a lot of normal vehicles? Cranking amperage somewhere between 300 and 600 amps. So if everything is scaled correctly here and set up as it should be, what we can see is we're going to essentially, the amperage should go up if we have our amp clamp is set correctly. Our voltage should go down, and that will not be anything we need to tamper with. But you can see here on the channel, the invert toggle is not on. The amperage channel is not on invert, and we're set to current and is DC current. So we should be ready to do our cranking event now. Now, the other thing you can do if you are operating on this and doing this job solo is you can use the trigger. So what I use when I'm going to do a trigger to do this test is I'm going to go into the time base. I'm going to lower the time base to 100 milliseconds temporarily. Once I'm in 100 milliseconds, I'm going to set the trigger. So I tap on trigger. I'm going to choose which channel I'm triggering off of. We're going to choose channel 1 because that's our battery voltage. And we know for sure that when battery voltage, what happens to the battery voltage when we crank the engine? It goes down, correct? So that's an easy way for us to set a trigger. So we're going to say our source is channel 1. It's going to be an edge trigger. It's going to be based off the falling of the signal, not the rising, but the falling, because the voltage is going to drop, correct? Then, after we do that, now the scope is going to enter into single sequence mode. So we're going to change our time base back out to, we'll just do 1 second because that should work just fine. And we're going to hit single sequence on the very bottom. Now, we didn't set our trigger level, so that's my mistake. My apologies. I got ahead of myself. Go back to 100 milliseconds. We're going to set our trigger level. And now we have to actually tell the scope what is the level of the trigger. So in doing that, we have to move this around a little bit. The trigger is right here on the level part, over on the far right of the screen, just to the left of the individual channels. So we're going to tell the scope, hey, we would like you to start capturing data when the voltage drops, we'll just say below 11. Because our battery voltage is what, 12-ish right now? 12 and change? So if we set the trigger to 11, as soon as that vehicle starts to crank, the scope will capture it. And the scope will always capture a little bit before and then a little bit after, however much you put as far as the trigger is set. Once you set the trigger, you can change your time base back out to a longer time base. When you do that, now what should happen is, we're going to hit run, we're going to hit single sequence, and assuming I have this set up correctly, we should be able to crank the engine and actually see what happens here. All right, so let's go ahead and do it. Here we go. And now it's always going to take the scope a minute to populate the data. So don't be alarmed if you watch the scope and you're like, hey, nothing's happening. It might take a moment for the data to actually come up on the screen, assuming I didn't screw the test up, right? So let's give it a second here. And now it's probably going to break it, right? I probably did screw the test up. This is always how it goes when you try to orchestrate something like this. So I'll go back to the trigger. We'll go over to 100 milliseconds. We'll set the trigger. Okay, we've got that correct. We'll just say dual. Maybe it'll trigger correctly if we do that. All right. So we got our voltage set. We have everything set up here. Now it should still do the test, unless the trigger is going to be a jerk and not cooperate today. But either way, you should be able to see what happens. There's our test. Whoop, we've got our amp clamp backwards. So when you do the test, if your amperage is backwards like this, you have two options. One, you can flip the amp clamp around physically, or two, you can go into the channel settings and just hit the invert button, and then simply repeat the test. Now you notice we don't need this much time on the screen, so we could actually shorten our time base up a little more if we wanted to, and then we could hit our single sequence button again. You notice our voltage is a little off the screen here, and we're going to go ahead and kill the engine. And we're going to hit our single sequence button again. And now the scope should wait. And we're going to go ahead and do this test. So you should see it populate here in just a moment. Assuming I did it correctly this time. Let's see if it actually cooperates, right? And it looks like I corrected it. All right, let's try it once. Now again, we've got a completely normal vehicle here, so nothing to be concerned about in that regard. All right. So since our current is going to go up instead of down, we can move it down there. We're going to hit stop. We're going to hit run. We're going to hit single sequence. And then we're going to start it. And now you can see we have our time base a little bit too narrow. So we'll widen it out to 2 seconds. We still have a plenty high sample rate. And we'll do the test once more. So you can see sometimes you got to do it a couple of times to get your settings perfect. And there we go. Now, we got a good one on the screen. So now, the scope will stop. We'll hit the stop button. And now what we can do is zoom in and look at what we're looking for. So here, we're zoomed in pretty far. Remember, we looked at 500 milliseconds before. We can now use our menu button here, and we can go into the measure parameter. We can select channel 1. We can take a look and we can say, hey, you know what? What is the lowest point of voltage when we crank this engine? 10 volts. If we turn on our cursors and we select the channel 1, drag our cursor up, 10 volts. Okay, perfect. What about our current? Let's change our channel for the cursor, or we can go back in and do the measure. We're going to select channel 2, and we're going to say our maximum current. Oh, we already have that turned on. 645 amps. Now, if we want to verify that, we can use our cursor. Here's our cursor. Turn it on. Drag our cursor down. Maximum current flow to the starter, about 600 amps and change. 660 or so, 645, somewhere in there. So again, no issues with this vehicle currently. If we want to zoom in, we can just use our time base like this, or we can also hit the zoom button, and the zoom button will allow you to see the bigger zoomed out picture on the top, and we can drag the window back and forth. And the zoomed in time base, we can see by manipulating back and forth down here on the time-based controls. So you can see we can easily get this waveform on the screen using the trigger. Now, if you want to use this a different way, if you don't want to use the trigger, you absolutely do not have to. Now, I've used it both ways. I've done it without the trigger before. If you want to do it without the trigger, then I would just recommend you put 2 seconds of time on the screen like this. Get ready to hit the start and the stop button relatively quickly. we're also going to lower our voltage down here a little bit. And we're going to change our scale for the voltage. Whoops, I just moved the wrong one. Time out. All right, so we're going to move our current to here. And then I'm going to select the other channel. And I'm going to drag that voltage down here until we're in the screen. So we're starting right there. And now we should get a little bit higher resolution picture because I changed the scaling on here to 1 volt per division instead of 2. So if you want to get a little bit clearer or higher resolution, then you can always play around with that setting. So what we're going to do is we're going to hit stop on the scope. Then we're going to hit run, and then we're going to do the test, and then we're going to jump back out of the car and stop the scope. So this is how you could do the test without the trigger. All right. And we can hit stop. And now we can zoom in and see detail on the picture here. Oops, zoomed in a little too much. So once again, you got just a little below 9.6 on this one. So minimum voltage 9.4, maximum amperage we got 610, so a little bit less. So again, if we wanted to repeat this test a few times just to make sure we didn't have a problem, we could do that. Now again, we're not going to put a lead on the starter today, but if we wanted to do that, what would we be looking for on the starter itself? If we're trying to find out if the starter has a problem, we should see that the voltage at the starter does not fall off dramatically and lose its supply, right? Now it's going to look similar to the battery. We're going to see a similar picture. If we see, for instance, a major fall off of voltage at the starter, let's say the starter voltage falls to like 1 volt or 2 volts, then that would likely indicate that we have an issue in the primary starter cable between the battery and the starter, right? You could also look at that on the control side. If we were connected to the solenoid terminal, again, we're going to expect that voltage to fall the same way we see it at the battery, not at a more dramatic level. If we lose, for instance, more voltage going to the starter control wire, aka the solenoid, then that means there could be resistance in the wiring between the starter solenoid and the relay, is typically how those are controlled, or there could be a problem with the relay itself. So again, we can add more tools to this particular test in order to increase the clarity of what the data physically tells us. But again, as you see, we perform the test several times here, and we get very similar results. Our voltage didn't fall much lower. Our amperage didn't climb much higher, stayed pretty constant. We could repeat it once more just for the heck of it, right? We'll zoom back out to 2 seconds per division so you can see it here. And we'll go ahead and we'll crank the engine and you can see what happens. So again, we've already done this test 3 times. Are we going to get similar results? Assuming the vehicle's normal, we should, right? That battery is going to lose a little bit of voltage, so that's not abnormal. All right, so let's go. What do we get? 9.372 or 27. So we do get a little bit of loss of voltage, right? That battery has been stressed a few times, but we still get a quick recovery on the voltage. And we see the starter amperage doesn't really go a lot higher. We're still right at about 612 amps. And we see that that amperage comes back down pretty quickly, as well as drops to a point where it is about half or a little less than half of the initial kick. So again, totally normal vehicle. Now, I don't have a broken vehicle to show you today, unfortunately. So do we have questions on any of the stuff we've gone over here? I'm watching the chat, so I'm not seeing any questions, but I'm just double checking here. And I don't see any questions in the private chat. Just going to check and make sure my other messenger portal. See if there's anything there. So no other questions. Cool. Well, you can clearly see how this is going to be a useful test. If you have a marginal battery, you're going to be able to pick that marginal battery off a lot easier using the oscilloscope than if you are dealing with strictly just normal conventional testing methods, right? So ultimately, again, just to go over what we have here for setup, we had one scope channel with the positive lead over here and the ground lead over here. So we're across the battery on one scope channel. And the second channel is an amp clamp. And the amp clamp is going to be placed preferably on the starter cable. But if we cannot get to the starter cable, you can place it around either of the two battery cables in their entirety. When we're doing that, it's going to be, you're probably going to install the amp clamp on the battery and it's probably going to be backwards. That's usually what happens. If that is the case, it's not a big deal. You remember how we inverted it on the software. We always want to see the current flow upwards on the scope. And so if that's what we're seeing on the scope, if it's flowing the opposite direction, we just open up the channel, hit that invert button, or come over to the car and flip the clamp the other way, and now your current flow will show up instead of down. So again, just some simple basic things to keep in mind there. So hopefully you've had a pretty easy time following along and seeing how we can use the scope for this dynamic starter test and battery test. I hope you found this valuable and educational, and you feel like maybe you can use your scope a little bit easier. We also showed you how to scale your amp clamp more effectively, and we also covered how to use the trigger function. Remember, when you're setting your trigger function, you do have to go into the time base. It has to be 100 milliseconds or lower in order to set the trigger. You don't have to be zoomed in that far in order to actually use the trigger. You just have to be zoomed in that far in order to set the trigger. So once you go zoomed in and you set your trigger and you tell it whether you want it to be a falling edge or a rising edge and any other type of trigger you want to use, once you set that, then you can zoom back out to a longer time base. So hopefully you found this educational. If you would like to see other specific types of scope tests on future videos, we will definitely be glad to cover those in the future. Definitely plan to show you some more scope related content in the future on the various live streams that we do. So just want to say thanks for taking the time to come out here and spend some time learning and understanding how to use use the Topdon oscilloscope more effectively. Now, today we were demonstrating on the Phoenix Max, but it is important to keep in mind that the Topdon oscilloscope will work on all the Phoenix Professional Series tools that have a normal flat USB port. So that would include the Phoenix Max, the Phoenix Smart, the Phoenix Elite, the Phoenix Plus, the Phoenix Plus 2, the Phoenix Lite 3, and the Phoenix Lite 2. The X-Link does not work. The Nano does not work. I'm trying to think if there's any other tools. The remote does not work. So it specifically has to be, again, the Smart, the Max, the Elite, the Lite 3, the Lite 2, the Plus, and the Plus 2. All of those tools will work with the Topdon oscilloscope. So again, we were demonstrating on the Max, but the general workflow that you're going to see and everything we demonstrated today will apply to using it on any of those tools. And you should see essentially the same screen, although maybe scaled down a little bit smaller on the smaller tools. Again, the Max is obviously the best user experience since it has the largest screen. So really appreciate everybody taking the time to come to the training today. And of course, if you got questions or more ideas that you would like to see us cover in future webinars, we are always interested in your feedback. And we do sincerely appreciate you taking the time out of your day to try and learn how to use the tools more effectively. So as always, I'm Hawken with Topdon, and thanks again for coming to our webinar, and we'll see you on the next one.